Got it. All right, so it's a great pleasure to have Christian Miniatura here for this seminar. Christian has been, the director of MajuLab here in Singapore. Kind of the outpost of CNRS in Singapore. He's been a fearless leader of the operation here, really kind of pushing forward interactions between French scientists. French physicists in particular, and people here in Singapore, both in NTU and NUS and CQT in particular. He's a theorist, has lots of very interesting ideas that span mesoscopics and even some more CQT-like things. And it's a great pleasure to hear what he has to say. So if you could share your screen, we'll be very happy to hear your question, your seminar.
Okay. So thank you, Justin, for the introduction. Okay, you tell me if I can start or not. Huh?
Yes, please. Okay. Yes, please.
Okay. Yeah. So yes. Okay. So thank you. Okay, I'm going to talk about, kind of recent development in a way, because there are two works. I think I don't know if I will have time to target the second work about Floquet system, but the topic is the same. It's about thermalization and condensation. I will just be flying over localization. It would need, a seminar by itself. Okay. And so this is a work we started back in 2015, and we recently, submitted a paper on the Floquet system. Okay, so and I will be down to earth. Okay, because starting with a very short and far incomplete introduction to the topic. Okay, so the scientific challenge is easy to state. Okay, so it's understanding the non-equilibrium physics of interacting system. Okay, classical and quantum, of course. Okay. And you have many ways to take a system out of equilibrium. I give some, okay? So you can apply a driving field to the system, or pumping energy into the system. So applying a driving field will be the case of the Floquet system, for example. And kicking the system more exactly. Inject particle in the system through external reservoir. This is a transport situation, and a sudden change of parameters, which is a quench. Suddenly you kind of switch on an environment for the system, and you let it evolve in an out of equilibrium situation. So in fact, in this talk, I will essentially speak of a numerical exploration of the mean field, in a sense, Gross-Pitaevskii, non-equilibrium, unitary, this is important, unitary dynamics of quantum waves, and non-dissipative Hamiltonian system. I saw that Jesus Schrödinger Perez is in the audience, so I will not target systems like polaritons or things like that, okay? So I deal with really Hamiltonian system without dissipation. And the two case studies that I will consider is an isolated interacting quantum system in a quenched static disorder, static is important, and a closed, periodically kicked interacting quantum system. So the particle number is conserved, and energy is conserved in the first case, and we will see quasi-energy is conserved up to multiple of 2 pi in the second case. Okay, and what is important is we look at situation where the equilibration dynamics is in fact self-induced by the system. And the experimental motivation is quite strong. In fact, our interest was originally motivated by nonlinear optics. I will briefly mention that. And with a view on cold atoms, okay, because of course it's a natural platform where you can control a lot of parameters, okay. So this is a context, okay. And in fact, when we started to work on the topic, we were not experts, and I must say we are still not experts in the field because it's a huge topic, okay. So let me start by thermalization in interacting classical systems. So thermalization is just the process of physical bodies reaching what is called, thermal equilibrium through mutual interaction. So I guess most of you, have gone through physics training, so you can have, some keywords flashing in your head while I'm speaking. So the classical kinetic theory tells you that the collisions induce between particles an irreversible evolution towards a thermodynamic equilibrium, and you might have in mind some keywords like Boltzmann H theorem, ergodicity, chaos, integrability, etc. So generally what we do, you take a classical gas or particle in a box, okay, and you have a random elastic two-body collisions, okay, collisions between the particle, which are supposed to be very brief, and of course interaction with the walls of the box. And typically, this is what you can see here. You have the two incoming particles with momenta P1, P2, and collisions, and you're exiting particles with P3 and P4, and you conserve the momentum and you conserve the energy, okay? So there are, I mean, many developments in this thermalization and classical kinetic theory. So some of the keywords is Boltzmann transport equation, kinetic theory of gas, Maxwell-Boltzmann distribution, thermodynamic limit, molecular chaos, etc., uniform maximization of entropy, equipartition of energy. So, I mean, speaking about that would be too long, okay? So I'm just flashing words, okay, so that you see the context, I would say. One thing which is important is that the process of thermalization erases the local memory of the initial condition, okay? So now the question is, okay, this was for classical, very brief, as I said, and far incomplete introduction, thermalization in interacting quantum systems. So this is a very hot topic indeed. And the question is, can an isolated quantum system be accurately described using equilibrium statistical mechanics? So can systems initially prepared in far from equilibrium states evolve in time to a state which appears to be in thermal equilibrium? And you might maybe remember, for people interested in the field, these beautiful experiments done in the Bloch's, Emmanuel Bloch's group back in 2016, and published in Science, where with atoms, you can see that there is this kind of blockade, I mean, related to the phenomenon of what the people call many-body localization, okay? So where you can see that the system can, in some situation, okay, so there are the parameters written above, where you start all the atom in this part of space, okay, and you let it evolve, and you see that the cloud of atoms expand, okay, so and here it does not, or less, okay. Okay, so it seems that quantum system may not equilibrate after all, okay? And this is coming, so to say, as counterexample to a famous hypothesis that was put forward, is the eigenstate thermalization hypothesis. And the statement is the following for this hypothesis, I insist, for an arbitrary initial state, the expectation value of an observable will ultimately evolve in time to its value predicted by the micro-canonical ensemble. So the dynamic, the self-dynamic of the system self-equilibrates. This is this ETH statement. And so what you do is you take the Hamiltonian, you solve for the eigenstates, okay? And now what you say that you take an observable and you take the expectation value of this observable between two eigenstates. And essentially what the ETH tells you is that it's almost diagonal. Okay, so you have an average value almost diagonal, and the fluctuations, in fact, goes to zero as the dimension of the Hilbert space, I mean, increases, because you know that it grows exponentially with the system size. Okay. So, as I said, there is an active research in systems escaping thermalization. I mentioned about many-body localization, which I won't go into the details, okay? But also in some other system, like a chaotic system and the phenomenon of scars, okay? Okay, so now I was essentially mentioning particles, even if quantum system, you can speak of wave. Let me mention now thermalization in interacting classical waves. Okay, and you can see that in nonlinear optics, because in nonlinear optics, people are dealing with nonlinear Schrödinger equation, and generally you consider a wave propagating in a uniform medium, but the index of refraction depends on the intensity of the wave. So you have a term which will be of the form g psi to the power 4, or interaction term. In fact, the term would be g modulus of V square, the intensity times the electrical field. And this is essentially what we know in cold atoms as the Gross-Pitaevskii equation. Okay? So what is the setting? The setting is quite similar. In fact, so you have waves now that interact through these nonlinear terms, G psi 4. And still you conserve momentum and energy. Okay, so momentum is related to K, H bar K, if you speak of the photons and so on. And what happens, and I will come back to that later, I will tell you how we derive, in fact, this equilibrium distribution. There is a formalism known as a wave turbulence theory in this context that people have developed, because, I mean, these classical waves, it can be nonlinear optics, but it can be also water waves and things like that. Okay, so there is a huge community working on this type of theory, of wave turbulence theory. And if you apply, you crank up all the recipes, okay, you find that under some conditions, of course, and frankly, the derivations are sometimes very, I would say, tedious, okay, and I'm not sure that I master all the detail myself, okay, but within a certain framework, depending on some approximation, blah, 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 you find that the equilibrium distribution is given by the Rayleigh-Jeans distribution, and the Rayleigh-Jeans distribution is just given here. It's essentially the temperature divided by the energy plus the absolute value of the chemical potential. And this distribution maximizes the entropy, okay? So since you have wave, I mean, a natural question that you have is, okay, yes, but since we have bosons, okay, could we imagine having a kinetic condensation at T equals 0? So it would be kind of a condensation, classical condensation, okay, at the lowest energy. And this would happen if you heat mu is equal to 0. And we will see that later, okay? Okay, so yes, in fact, this has been observed in some experiments, even if you can debate, because there is always the question of the thermodynamic limit lurking behind, of course. So the people, they took this homogeneous nonlinear medium and possibly a trap, a fiber, for example, okay, where you are trapped inside a fiber. And importantly, you start with an initial random field. That is to say, the wavefront is completely, I mean, with a lot of corrugation, if I may say, okay? And you start, so you shine this random wave, initial field, and you send it in this homogeneous medium, nonlinear medium. And what you see that there is indeed macroscopic occupation of the lowest mode of the cavity or of the system. Okay, so here is an experiment done with dye. So here it's a dissipative system. So I won't talk about that. The situation I want to consider is more the second one, where you see you shine a laser light, and you have, in fact, you have kind of glass. You have you take a window, you break the window, whatever. You shine light through this medium, so the wavefront is completely random, and then you shine this random light into this here you see with V into this material, nonlinear material, that, and you control the nonlinearity with some electrical voltage. Okay, and you look in the far field, and you see that you have here what is happening. Okay, or far field or not, depending on where you put the lens and all of that. Okay, and so in Fourier space, this is what you see. You see something which is extended, and little by little, you see something growing, and a macroscopic occupation. Okay. So the question now is, what about disordered system? And this is how we came into the field, I would say, because some of our friends back in France were working in this nonlinear business. Okay, and in particular, in the previous experiment here, I have a friend, I mean, being co-author of this studies. And they wrote, I mean, a report, okay, about optical wave turbulence. And in fact, towards the end of the review, they speak of, there is a short, quite short paragraph, I would say, thermalization and condensation in the disordered system, where they just point as thermalization in a random potential is expected to be strongly affected by the spatially localized nature of the Anderson modes, of the underlying Anderson mode of the linear system, okay, of course, okay. And so they were saying that it's a natural important question to be addressed. And in fact, this is what we have tried to do, at least from a numerical perspective. So I recap here what is the usual optical wave turbulence theory. So you have a homogeneous Kerr medium, and you send a random phase wavefront. And this randomized wavefront plus the wave mixing, the nonlinear term, the interaction, leads to thermalization and possibly condensation if you have the right regime of parameters. So our idea was, so I'm working in the field of disordered system. So I say, okay, I'm taking my hat as disordered physicist, okay? And in our field, generally what we do, we take an initial perfectly coherent field, a plane wave, and we let it evolve in a disordered potential. And so we said that the disordered potential by itself should randomizes the wave, okay? So what happens if you have at the same time the disorder, but also Gross-Pitaevskii equation? So could we observe also in this system, so a Gross-Pitaevskii equation in the disorder, can we have condensation, thermalization, and possibly a condensation, okay? So what is the physical and numerical framework that I will explore? Okay, so what we need, which is important to understand also, is that we need a global excitation of the system, a plane wave state. Okay, because if you take a wave packet, as the wave packet expands, it becomes diluted. Okay, so I mean the interaction term, you remember G psi square. The psi square is decreasing. Okay, so you would lose the interaction term will decrease in time in some. So you don't want that. So you need a global excitation of the system. The wave is everywhere, and then you subject it to a random potential. So here I show it in 2 dimensions. Okay, so you have a particle, this method, and you solve Schrödinger equation where you have a disorder potential. So you can choose any type of disorder. Generally, what we did is to take a speckle pattern because this is more relevant to experiments. And you have repulsive interaction in the term of a Gross-Pitaevskii term. So you can characterize the disorder with these 2-point correlators. So you define a correlation length, you define the disorder strength, and so on. And what we were interested in is, do we have any evidence on the momentum distribution? So you solve the equation, you compute in Fourier space, the psi of k, you take the modulus square, and you average over all disorder configuration. So this is our observable. Okay, and why do we choose this observable? Because it's measurable in cold atom physics with time of flight measurements. So the question is, what is the time evolution of the disorder average momentum distribution when the interaction is absent and when it is present? And of course, you can imagine that you can let the atoms evolve in the disorder without interaction, and then switch on abruptly the interaction, even if it's maybe not very easy to do in an experiment. So I will briefly fly over this non-interacting case when G is equal to 0. So you have a Schrödinger equation in a random potential, okay? And essentially, from a particles picture, what you get is diffusion and ergodization. In fact, the propagation of the atom in the disordered potential, it bumps into all the potential in the potential landscape. And it looks just like a pinball game. So you start here, classically you start here, you see you have a very complicated path, a scattering path, and you end up here when you look at it. And essentially, you can show that macroscopically, you get a random walk and a large scale motion is diffusion. So you have an ergodization on the energy shell. And what you expect when you do that, you expect that the momentum distribution has this ring-shaped kind of volcano structure. The radius of it is just K0, okay, the initial momentum of the plane wave, okay? So this is ergodization due to the scattering, okay? So, but you have wave. So in fact, you have interference. And we know that the disorder average do not scramble all the interference effects. And in particular, you can observe 2 signatures of coherent transports, okay? Namely weak and strong localization. So weak localization is more that you see interference effects, okay, but you may be diffusive, still diffusive, okay, And CFS, the coherent forward scattering peak, is when you get strong localization, that is to say Anderson localization with localized modes. Okay, so how does the CBS happen? Okay, but, on top, this is a numerical experience. On top of the volcano ring, you see a peak appearing exactly at minus K0. So it's a retro reflection, if you will. Okay, so if you observe that, and it has been observed in experiments, okay, you have a clear signature that you have interference in your system. So you don't have any dephasing mechanism or whatever. Okay? The transport is coherent. And in the right regime of parameters, okay, then you can see localization is witnessed, okay, by the emergence of a second peak, which is twinning, in fact, the CBS peak, called the coherent forward scattering, K0. And this is what we discovered in a publication in 2012. And in fact, this CFS peak is capturing the critical exponent of the Anderson transition. It captures also the multifractal dimension and all of that. Okay, so I will not speak about that. But typically, when you are in the Anderson localization regime, this is how the momentum distribution looks like. You have, isotropic diffusive ring, volcano type, and on top of it, two horns. Okay, this is what you should get. So this is a starting distribution. Okay, so now I say, okay, we are going to switch on the Gross-Pitaevskii term, G psi square, and I will assume, and we'll see later why, that the magnitude of the nonlinear term, which is given by G times the density, the number of density, is much less than the disorder strength. And again, I insist, so weak interaction regime. Okay, and I insist, okay, we have a global excitation of the system, a plane wave state. Okay, so now, you need to think a little bit about the time scales, okay? And here we have the collisional time scales and the isotropization time scale, okay? So collisional, it means here you see that when G is not equal to 0, so let me come back to the one. In fact, you can see this G psi square as a disordered potential also, fluctuations, okay? Because psi evolving in disorder is randomized, so the G psi square is also randomized, okay? And it depends on time, okay? So, so in fact, you can see, I will not detail the theory how you do that, okay? It's important to have more in mind the ideas. Collisions, they will redistribute energy over a time scale, which is given by, which scales like the inverse of G square, okay? And this is what we call the thermalization time, okay, or collisional time. Okay. And from our previous studies with the linear system without the interaction, the fully developed diffusion, the ring-shaped structure, volcano-shaped structure in the momentum distribution is established after the transport Boltzmann time, which is scales like the inverse of the disorder strength to the square. Okay, so we have these two times scales. I told you that the G psi square is fluctuating, okay, in time, and you can show, or at least numerically show, that the nonlinearity in fact challenges the Anderson transition in the sense that it will induce a dephasing between the scattering amplitudes and the interference leading to the Anderson localization phenomena. And people have studied, in this paper that I mentioned here, have studied the time it takes to get rid of these interference terms, known as the dephasing time, and it scales like 1/G. Okay, so you see you have three time scales, and now as good physicists, we have to compare them, okay? So the regime of the weak nonlinear regime, the time scale hierarchy is the following. What you want is that the dephasing time is much less than the collision time, 1/G, much less than 1/G square, so that you can discard very quickly interference effects. So you can forget about CBS, CFS in momentum space. Okay, so you see that it means that G is small. Okay. And what you would like that the randomization of the wave front happens much earlier than the redistribution of energy. So you want so to say, reaching the diffusion regime in a way is before you can redistribute energy. So you want to impose also this term. And you see this amounts to G much less than V0. When you put everything with a scale, it's Gn much less than V0. So you have the situation where you have a disorder that isotropizes the atomic momenta very fast before nonlinearity can start to play a role. This redistribute energy, and the nonlinearity will itself, discard or wash out interference effects. So let me just briefly mention, I don't want to be too technical, but maybe to flash how you would process about the case, for the theory. So you take your state, of course, you expand over the disorder eigenstate. So the disorder, you take one configuration of disorder and you solve for the eigenstate, and you expand. And of course, you have a normalization condition. And here you take care of the number of atoms because you have an interaction, G psi square. So the number of atoms is important. So you can define the non-interacting density of state, which is built upon the eigenenergy of the non-interacting system. Here you have the volume. And the bar is always the disorder average. You do that over many disorder configurations. Now, so now you need to define the energy distribution. So in fact, it's just, I take which are the eigenstates which have the energy E. So you have the delta function here. And of course, you put a weight, which is corresponding to the corresponding weight on the corresponding eigenstate. And you have a normalization factor in the denominator, because you impose a normalization, which is written below. So these are the quantities that you need to consider. Sorry. So what is the momentum distribution? The momentum distribution is easy to write. So you have an integration of all possible energies of this energy distribution that I have defined here. And you have, another quantity, which is the non-interacting spectral function. Sorry for all these technical details, which is defined here. Well, I don't want to go into the details. But we can compute all of that. This is what I mean numerically. So now you scratch your head and you say, that is fine, but how could we develop a wave turbulence theory in the weak nonlinearity regime? A la Boltzmann transport equation. So you can do that, and in fact, you can show that the time evolution of this energy distribution obeys kinetic energy, which is written here, where when you see that you have a collision kernel, in fact, this is the difficult part to write, of course, as always. What is the exact form of the collision kernel? You have the density, a product of density of states, energy conservation. Remember that we deal with two-body collisions. So you have incoming energy E1, E2, and exiting energies E3 and E4. And you have a detailed balance term. Because you feed the mode, you feed the energy distribution, and you empty the energy distributions. So writing the collision kernel can turn out to be really difficult, because it needs a lot of approximation. But one thing which is important is the following: as soon as you arrive at this form of the kinetic equation, you can easily deduce what is the stationary distribution, because the stationary distribution, you want to have the time derivatives to be 0. And in fact, it just tells you that you have to cancel the detailed balance term. So that is to say, you have really detailed balance. So it means that this equilibrium distribution should solve this equation, the detailed balance term. And in fact, if you divide by the product of the 4 energy distribution, you get to this equation. And with the constraint, of course, which is, let me go back, which is given by the energy conservation term, that E plus E2 is equal to E3 plus E4. And you can easily see that the solution to this equation is given by a term which is linear in E. So you have alpha times E, alpha being a constant, plus gamma, another constant. It's an affine function. And you can immediately see that it works, because when you plug into, all the gamma terms will be disappearing, cancel right-hand side and left-hand side. and the energy you get in the first term, you will get E plus E2, and in this term, you have E3 plus E4, and precisely, this is energy conservation. So if you invert and you massage a bit the equation, what you get is the Rayleigh-Jeans distribution, where you define a temperature, quotation mark, and a chemical potential. And of course, written in this form with minus mu. And of course, when you have since the equilibrium distribution should be positive for all the accessible energies, then it tells you that T must be positive and mu must be negative. Okay, at least when the energy are positive. In fact, to the minimum of energy, I should have said. I see that there is a question. No, okay, so sorry.
It's not a question, no.
It's not a question, but I wanted to check. Okay. So let me add also that the kinetic equation that I wrote before, okay, is in fact reduces to the usual two-dimensional kinetic, usual kinetic equation that you find for homogeneous medium and classical fields. Okay, here, okay, I'm insisting you see that you don't see the 1 plus F for the Bosniak amplification. Okay, so we are in a classical approximation also, so classical field, and this is what I will do. Okay. Okay, so now, I mean, it's very easy now to compute the equilibrium momentum distribution, you see, because you just plug the value for the equilibrium distribution, for the momentum distribution, you just plug in the equilibrium energy distribution. In fact, for technical reasons, you need a cutoff, which is precisely linked to the fact that you want to describe classical fields. I won't go into these details, okay? And of course, you may wonder, how do I compute now T, the temperature and the chemical potentials? Well, you need self-consistent equation, and these are easy to find because you know that you have a conservation of the total number of atoms. If you integrate n of k over all momenta, this is what you get. Here n is the density, the number density. And of course, we have, as I said, I mean, a conservative system. So you have conservation of the total energy. So if you integrate over all energies, you should get the initial energy, which is given here. Okay, so the initial energy is given by the initial kinetic energy of the plane wave, and also you have, I mean, this interaction term. Okay, so you have self-consistent equation that you try to solve and find if you can find a temperature and a chemical potential, and how. Most importantly, how they depend on the initial parameters, E0 and V0, for example. Okay, so this leads to a phase diagram that I present here for a 2D speckle. Okay, so here you see that here on the vertical axis you have the temperature, and here you have the initial energy E0, and without entering into the technical details. Okay, so you fix the density, because in the previous equation you have an n here, you have to fix the density. So here we took a certain density, say 2. And what you find is that there are two regions. There is a blue region where you can indeed find mu and t, non-trivial functions of the parameters, and which describe a pure thermal gas described by the Rayleigh-Jeans distribution. And this is what you see in the right panel, where you see this ring-shaped structure. Forget about the CBS, CFS, because of the dephasing. This is what you expect at the start. And then when you switch on the interaction, you converge very quickly. You should converge very quickly to this Rayleigh-Jeans distribution. And this shape, you see, it's kind of a bell-shaped curve. Okay. But importantly, if you are in this pink region, okay, you see that you cannot solve simultaneously the two equations. And in fact, there is a critical line, which is a boundary, of course, where you have mu is equal to 0. And in fact, inside, you keep mu equals 0. So one equation is fulfilled, you know that mu equals 0, and then you have the second one for the temperature. And when you look at it, you see that, in fact, this region describes a thermal gas described by the Rayleigh-Jeans distribution and what we call a BEC, but macroscopic occupation of the fundamental mode. Okay, so let me try to explain this. In fact, when you look at let me go back here. When you look at this equation here about the total number of atoms, in fact, it describes all atoms, in fact, essentially in the excited states. And it's back to the original Einstein argument. That is to say that the critical line mu is equal to 0, in fact, signals a saturation of the population in the excited states, which can no longer accommodate more particles. So you need to put the particles in the E equals 0 mode. Okay? So you allow for macroscopic occupation of the lowest energy state. So you have mu equal to 0. So now what you say to solve the equation, you need to update the equation. You need to say that the momentum distribution will contain a condensed part, okay, plus the remaining part, which is due to the Rayleigh-Jeans. Okay, so if you solve the equation, you will find that the number of condensed atoms would be given by 1 minus this function. And you see that the density of state divided by E, this is this factor that drives the convergence properties of the integral when E is equal to 0. Okay. So now you can come back, okay, and you see that so here I plot the density of states for the disordered system. Remember, the density of states appear here is for the linear system without any interaction. Okay. So if I had a completely homogeneous system, we know that the density of, say, for quantum waves in homogeneous system is without any potential is just flat. It's a constant. Okay. So if it is a constant, you see that you have dE divided by E. This is a constant. So you have a logarithmic divergence. It means that, in fact, you can always populate the excited states. So you need to modify to compensate for the divergence. Okay. And this is exactly what the disorder does for you, in fact. When you plot the density of state, you see that it goes to 0. And in fact, if you look close to the energy equal to 0, you find what is known in the field as the Lifshitz tail. So the density of state behaves like exponential minus 1 over the energy. So what we see, in fact, is a macroscopic occupation of the states in the Lifshitz tail of the disorder. Okay, can we have other signatures, or say, yes, signatures for the condensation? Okay, so let me look at here. I give you, I mean, it's a rough, I mean, numerical simulation that were done back in 2015. We never published them for some reason, okay? But not scientific reasons, I mean. So you start at equal 1, you see you have these peaks, the CBS and CFS peaks, okay? It's pointy here. After time 16, say in the right units, you start to melt, and then you see at later time, you see that you get a peak at momentum 0. And you see that it's kind of pointy. And indeed, if you try to model with a condensed and a thermal part, you can fit and you get a bimodal distribution, just like the people observed in cold atom with cold atoms back in 1995 when they saw the first condensation. These were the first signatures. Okay, so you could see a pedestal, the thermal background, and on top of it growing a peak. So this is exactly what we observe here numerically in this system. You have to note that we have a condensation in k equal to 0. Okay, so we are in momentum space here. Do we have another signature, possible signature? Yes, we have the Penrose and Sager criterion. So what we do, we define a one-body density matrix. But of course, if you do so, it's a pure state. So if you try to solve for the eigenvalues, you will only find one eigenvalue, 1, and the rest 0. So you need to coarse grain the density matrix, and there are many ways of doing that. You can here what we did is averaging over disorder might not be a good idea. But you can also average over a small range in space, a small range in K, small range in time. There are many processes, and these are well studied in the literature. And essentially, they give the same result. So you get this coarse-grained density matrix. Choose the way of doing it, and it's a Hermitian operator. So you can diagonalize, and you can see that there will be one macroscopic population, you see that you get one macroscopic eigenvalue and the rest is very, very small. So this is a strong indication that you have a macroscopic occupation of a single mode. And of course, this single mode, which corresponds to the associated eigenstate, would be the condensate, okay? And so you see that now what is a scenario? The scenario is that since we start with a global low energy excitation, this plane wave state, essentially it couples to the eigenstate of the disorder system, okay? And mostly to the localized states that reside in the Lipschitz state. And these states do not couple easily between each other with the interaction. And so it hampers thermalization and opens the route to condensation. The problem that we have is that these exponential states in the Lipschitz state are difficult to catch in numerics because they are in fact exponentially rare events. Okay, and the density of state is exponential -1/e. Okay, so you can see that they are extremely rare. Okay, but anyway, this is, I mean, the mechanism that we can see. Okay, I don't know how much time do I have, Justin, left.
Oh, you know, you can try like 10, 15 more minutes, perhaps. Okay. We like to have some questions, maybe like 10 minutes. So
okay, then fine. I have enough time. Okay, so then. Okay, so this is our study back in 2015. And now, I mean, recently with Gabriel Lemarié, who joined me at MajuLab in Singapore, we had the idea to apply this, to see if Floquet systems could enter the same type of physics, okay? So the question is, what is if energy exchanges are allowed, or you kick the system, so energy is no longer conserved. And in fact, it turns out that there is, of course, a huge literature on the topic, okay? And the non-equilibrium dynamics of interacting periodically driven quantum system has been under intensive scrutiny over the past few years. And in fact, the people were interested in some exotic stationary states that could emerge, and maybe you heard about time crystals, of course. Okay, so the worry we and the other people have is that yes, okay, but you have an interplay between interactions that redistribute energy, but the temporal driving also induces heating, yeah? Okay, because you inject energy in the system. Okay, you can inject energy in the system. So essentially, you force the system into a featureless state of infinite temperature. So how do you get around? Because this would not be really interesting. You boil the system. It's all. In fact, people devise many strategies. Think of many body localization, for example. Okay, coupling to a bath, high frequency driving, etc. So we had a similar idea, in fact, and if you are able to implement these strategies, you can see that the system can reach what people call a pre-thermal plateau, where the equivalent of this low energy physics that I mentioned previously can happen. Okay? So we wanted to give it a try with the quantum kicked rotor. Okay, so you have a quantum rotor, so you periodically kick with delta kicks harmonic, a cosine potential. Okay, so it's periodic potential, and you add interaction. And here, note that we added its interaction in p space. Of course, when you do experiment with cold atoms, the interaction are in real space, okay, in position space. Okay. The reason why we did that is it leads to simpler numerics, okay? And we are currently doing the same with interaction in position space. And typically what we find for now is very similar, okay? So, but let me present what is happening with size p square. And I'm not saying that it has experimental bearing for the time being. Okay, so when G is equal to 0, come back here. When G is equal to 0, I just have this Hamiltonian, and this Hamiltonian is very well known for the people doing quantum chaos. And it leads, in fact, to a phenomenon of quotation mark Anderson localization, but in momentum space, okay, which is called dynamical localization. Okay? And it means that the role of P and X, compared to what I said about the static disorder, will be swapped, in fact. Okay. So you have kicks happening at discrete times, okay, and you define the wave function just after kick n or before the kick n. Okay, so this is a notation I use. Okay, you have a normalization condition. Let me drop that. What is important is that starting for the Hamiltonian, the full Hamiltonian, even with the interaction term, you can show that you can derive, because of these delta kicks, you can derive a Floquet map. So you can relate what is the wave function right after the n+1 kick and right after and right before. So in fact, this is the kicking potential. You impose a phase on the wave function. And you see that you are in theta representation, in space representation. And if you want to go from the right after the n kick to just before the n+1 kick, so you don't have the potential, which is key, but you have the interaction term, and then you can write the evolution equation. So in fact, we know from this Hamiltonian that the effect of the kinetic energy is well reproduced by replacing it with random phases. In fact, in a certain, and you can, the disorder strength is the extent, the random phases varies in between minus W and W. So you see that now you have a map. Okay, I start right after the nth kick here in P. I evolve before the n+1 kick and P. I need to do a Fourier transform to go to space. Once I am in Fourier in the position space, I impose this phase here. I get right after the n+1 kick. Then again, I Fourier transform back to P space, and I chain all that Floquet maps. Okay, so numerically, it's easy to do. Okay, so now the theoretical description is really, I mean, paralleling what I did for the disorder. You just have to introduce the Floquet mode of the system. So you have a Floquet Hamiltonian, which is the kick Hamiltonian without any interaction minus I dt. You define the quasi-energy in this as the eigenvalue, eigenfunction and eigenenergies of this Hamiltonian. You expand the wave function over this linear Floquet mode. You define exactly in the same way the energy distribution. You have the same type of normalization. The important thing to remember now is that here we have a periodic system. So we have quasi-energy bands, just like you have Bloch bands in solid state physics. So you have a band with a certain extent. It turns out that the extent, when you do the math, is 2 times k, the kick strength, plus W, the disorder strength, and they are separated by 2 pi. Okay. So now if you try to derive a Floquet kinetic equation, you can follow the same type of reasoning, but now you don't have energy conservation, or more exactly, you have quasi-energy conservation, and this comes with up to multiple of 2 pi. Okay. So you allow process where the energy, quasi-energies are conserved up to multiple of 2 pi. So this is a new term, and this is a term precisely which is responsible with boiling, because it is interband transitions, in fact. So the question is, can we strongly suppress these interband transitions? If we can do so, then we essentially back to the quenched static disorder. And yes, we can do that. And the reason why we can do that is because of the density of states that you see here. There is a simple argument, in fact, a convolution argument. You can show that if this quantity, which I call ED, which is K plus W, so half the bandwidth, is less than pi over 2, then boiling is strongly suppressed. So essentially, you stay at m equals 0 in the m equals 0 sector. Okay, and then you are back to the previous case, and then you allow low energy physics, pre-thermalization, and so on. So let me flash some numerical result that we got. So at time t equals 0, you see that we get this CFS and CBS peak, okay? Except remember that they happen in real space now, okay? Because I told you that space and momentum are reversed for periodically kicked system. And as time proceeds, you see that there is a melting. This is a dephasing mechanism, killing these interference terms. And you see that you melt also in the middle at T2 equals 0. If you look at the position variance of the system, you see that the position variance of the system gets flat for a very long time. It's a logarithmic scale. And this is in this plateau where you can get this low energy physics happening. Okay. So let me show you what we get numerically. So this is the, so you let the system evolve. Okay, so when you are, so you compute let me go back here. So you try to compute this quantity that I write here as a function of time. Okay, as a function of time, you have the map. So you can do that. And at long time, when you enter, sorry, the pre-thermal plateau here, when you enter this plateau, what you get is the perfect Rayleigh-Jeans thermalization distribution. So this is the blue dots are the numerical calculation, and this is a fit using the Rayleigh-Jeans distribution. So it works beautifully well. And here it's the distribution in space, and you see the blue dots and error bars are given is a numerical simulation, and the red curve is the one that you obtain from the parameter T and U that have been extracted. So yes, we can also witness Rayleigh-Jeans thermalization in Floquet system, provided you can strongly suppress this interband transition. Note that suppressing does not mean you completely kill them, but because you see that at some point there is a boiling of the system, and the way the boiling is happening is something under investigation. Okay, it's not yet clear how it goes. It might be a higher order process. Okay. So let me see what happens when you get closer to the band edge. Okay, the lower band edge. Okay. You see that if you plot the energy distribution now, it departs from any attempt to model it with the Rayleigh-Jeans distribution. And if you produce, I mean, you do compute the Penrose-Onsager criterion, this is a population gap. That is to say, so you order the eigenvalues of the one body density matrix. You take the largest minus the second one, okay? And you see that you have a macroscopic difference, macroscopic 0.5, 1/2, okay? So, but still an indication that you have a macroscopic occupation of the lowest mode near the lower edge of the band. And if you compute the spatial distribution, you can see that it is bimodal. Okay, and you see that, and here is the Rayleigh-Jeans distribution that you get, fixing mu is equal to minus ED. Remember that the band edge for my system with a quench static disorder E was 0, so mu was equal to 0. Okay, and so there is a strong indication of this classical wave condensation in the leaf sheet tail of the Floquet system. Something that I want to mention also, you might wonder, okay. Here it seems that the condensed part has a width in theta. Yes, it's true, but it has no width in P. So if you compute the distribution, that you see that it is completely flat. So in fact, it's completely extended as a state. Okay, so let me go to take-home messages and perspective. So Gross-Pitaevskii interactions induce dephasing and lead the system to a thermal Rayleigh-Jeans distribution. Disorder, be it in temporal or in space, okay, seems to enforce a condensation at low energy states for suitable parameter values, contrary to the homogeneous case. The full distribution that you observe is bimodal, and the Penrose-Onsager criterion seems fulfilled. So what we would like to address now, of course, is a detailed analysis of the dynamics of thermalization and condensation, a real kinetic theory, okay, which we didn't do, in fact. Okay. What is the real fate of localization? Because you see, I am kind of contradicting myself, saying that there is a dephasing time killing the CBS and CFS effect, but at the same time, I'm building my theory on localized modes. Okay. What is the, we should do an analysis of the condensate state, that is to say, a scaling with a size. Okay, so the scaling with a size looks okay for the flow case system because you see n is a size here. We go to very large sizes and it looks flat. Okay, it's less clear. It's less clear for the point disorder. Okay, and of course, one thing that you may address: what is the connection to superfluidity? And since we have, for example, for a 2D system. Do we have the equivalent of the BKT transition, okay, or not? Okay, and it seems that we have. Okay, there are recent works addressing this question, and it seems that we can enter a BKT-like regime. Okay, last slide. My previous collaborator. This was on the localization, thermalization, everything. Okay, and the more recent one about this last paper about the flow case system. Okay, I thank you for your attention.
Thanks very much for this talk. Any questions from the audience, especially students? So let me perhaps start first, right? So in this last section about your dynamical localization through the skipped rotor, it wasn't super clear to me. Are you saying that the interactions, does that destroy the dynamical localization or not, or do you still get some? How do you identify it? Because you talked about the RJ.
Okay. The question is difficult to answer, but
I'm sorry.
Okay. No, it's okay. But you see, okay. So here, okay, what we do in this experiment, okay, we start the system in a plane wave, and we only let the kicked Hamiltonian act. There is no interaction. So we kick the system for a certain number of time, and well beyond dynamical localization sets in. So you measure the spatial distribution here, and you see the emblematic CBS and CFS peaks. Okay, this has we have studied that in another publication without interaction, so it works beautifully well. You have all what you need. Okay,
as expected from the kick.
As expected. So
okay,
so
good.
you have coherent transport, you have localization, everything as expected. Okay, so after you reach that time, okay, now you switch on interaction. So the system, so to say, is in the localized regime, and you let interaction play their role.
But is your kicked rotor still going on?
Yes,
are you still kicking?
You're still kicking. Okay. And so what you observe is that maybe it's not very evident with the color code, but you see that, so here time is proceeding, right? Okay, so you see that the peak is decreasing. So you see that the peak decreases, and at the same time, the momentum. Let me maybe go back to the one with the disorder. Okay, you start. Okay, you start with a pointy structure here. So so imagine that you have your volcano tap with the two peaks. Okay, so what I'm telling you is that the two peaks decay fast. Okay. And at the same time, the ring-shaped distribution is melting to adopt this kind of bell-shaped structure centered at momentum 0. Okay.
Okay, but do you still call that the pre-thermalized phase, or is it already thermalized?
The pre-thermalized is when you reach this one. Okay. So how do you call pre-thermalized? Okay. So as I said, you see the CBS and CFS disappear. So if you believe that CBS and CFS are emblematic of coherent transport and localization, they are washed out.
I see. Okay.
So we say that there is dephasing at work. Okay, and now you have redistribution of energy, and the momentum distribution is going into this shape that we try to quantify. Essentially, what the theory tells you, it should be Rayleigh-Jeans.
I see. So if I try to reframe what you're trying to say in terms of the MBL language, are you saying in this case here, the MBL phase of, say, dynamical localization does not survive some interactions? Is that what you're saying, or no? Am I misunderstanding?
I wouldn't say anything about the MBL phase, okay? Because here you see we are Gross-Pitaevskii. It's a different description.
So that's the okay. Okay.
It's a different description. So I just don't want to say anything about
you don't
MBL.
say anything.
I would be killed, okay? Yes, it would be interesting to find out, okay? But I just don't know, okay? Okay, so because I mean MBL is preventing thermalization, right? In principle. Okay. And
yes, that's right. But you're in your case here, it seems like it's killed, right? So
yes, it's killed. Yes,
you're killing it. So in the sense that if you are trying to induce localization through kicked rotor, which is like a Floquet kind of thing, the localization that you are experiencing is very sensitive.
Yes.
Even Gross-Pitaevskii like interactions.
Yes. And this per thermal plateau, the way we define it, okay, is we look at the position variance of the system.
Mm-hmm.
Okay, you start from a plane wave and so on, and you see that okay, there is an equilibration phase. This equilibration phase, you see the time scale 2 here, right? Correspond roughly to the time where you have the peaks have disappeared when you look at the above. Okay, so the CBS and CFS disappears, and then you reach. Okay, I will need to put on battery my computer. So if I disappear, don't worry. Okay. Okay. Okay, so, and then it's flat. That is to say the state does not evolve. And at some point, you see that it boils. And it boils, you see that the position variance is 3. And this is, you can see that theoretically, this is the maximum value that you get. Okay, so the important part is this plateau. And this plateau is when you get this kind of bump in the middle. Okay, this pre-thermalization plateau. Sorry, I lost track because of I was putting on the second.
No, you've understood. No, you've answered my question. My question really was, how sensitive was your dynamical localized phase in the context of MBL? That was the kind of question. Of course, you want to be careful with what you say, okay. But that was my question. I think you've
people have studied with spin systems. Huh? People have studied with spin systems how you can with the driving, okay, for the MBL, okay, because the MBL, okay, I was mentioning that. Let me say that I think it's important. Okay, I said that you have a very different strategy here. High frequency driving. Okay, so remember the experiment by block. Essentially, you have suppose you have wells, okay, and you have a hopping amplitude, right?
Yes.
Okay, between the wells, but you have also a driving energy, so you have the bands. Okay,
mm-hmm.
So you have in the same way you will have, since you are periodically driving your system, you have exactly the same type of physics, and in fact, what you want you want a fast driving. So that J, okay, so to say divided by M is small. In this case, you ampere high order effects, and you can have a thermalization happening. Okay, so the people have studied, I mean, really interacting systems, spin systems, and things like that. Okay, where you can do that. There are strategies to avoid that. Okay. How does it impact MBL and all of that? It's just the same. How does it impact localization? It seems to destroy, but what is going on really, I don't know. There are numerical experiments. I don't know any kinetic theory. What is interaction between the condensed part, the non-condensed part? You see, okay, how does it go? Okay, so to me, the picture is not yet clear. So I don't want to say definitive.
Okay, thanks a lot. It looks like Jesus has a
Christian, I was thinking in the first part you discussed that there are some characteristic times.
Yes.
My question is, suppose that in the second part you stop the modulation. And then you let the system back to its, let's say, linear equilibrium, and then you kick in again, do the, let's say, disordering and ordering of the system. Are those times the same? You understand what I mean? In your...
So you do what I did. So you get the Rayleigh-Jeans, say, for example, yeah. okay, and you stop, you switch off G.
Switch off there.
Okay, and you let the system evolve only with, okay.
And then you switch on again, and then you compare the two times. The one for, let's say,
now, we didn't do it. Okay. So I don't know how to answer that question. I don't know. In principle, I mean, okay. Again, here we start with this. Okay, the rationale without the G equal to 0. You start. Okay, we start, as I say, with the plane wave because the reason I mentioned about this global excitation and so on. Okay, and localization should be the norm, right? Okay, you should always have localization. But of course, I mean, there are some other questions. Okay, that is to say, how would you see what would be the time scales? Okay, to see localization. Do you want, starting from an initial state, whatever it is, okay, to reach the localization regime and then do again the same type of things? So what would you do? So this is what I don't get exactly. Is your question, okay, I start with the Rayleigh-Jeans, G is now 0, and I still kick. Do I observe dynamical localization? At which time scale do I recover the CBS and CFS peak? Okay, or not? Okay.
And what's the time? And what's the time?
Okay, so that I don't know. Okay, because you have to understand that. How would I say that? Your initial state, I believe, would have plenty of K.
Yeah.
So you don't start from the plane wave.
Yeah, because you start from the plane wave in your case.
So the distribution that you would get later, I would have to think a little bit how to interpret. Okay.
Yeah. Okay. Now I understand. The question would be: would you get the same result if you began with a, let's say, chaotic wavefront on a chaotic dispersive medium?
Yeah, but I believe we should observe the same type of. It should be robust. Okay, because the thermalization and should be robust. This is my feeling.
Okay.
But good suggestion. I mean, this is something we can investigate because we have the codes. So that's and this is why we put the interaction in P, because it's really simple to implement, and we can go very far in the number of kicks.
Okay, very good. Are there more questions from the audience, from students especially? All right. If there are no more questions, let's really kind of thank Christian for this excellent talk. You know, thank you very much.
Thank you.
So next week we have one more talk. It's the same time as well. So please keep coming for our condensed matter seminars, right? So thanks very much for your participation. Bye, guys. So Christian, actually,